Hello and welcome back to the lab. Today on the bench we have a second pass at the HP 5345A. This is a experiment that we ran in the lab, which, to be honest, has failed. One of the questions I get asked on the channel quite a bit, because for somebody who's new to the channel, these repairs seem to be heavy-handed, and I go in, I replace a whole bunch of components, it's preventative maintenance, things like that. And everybody's, I do get a lot of comments about, it's too much, the value's destroyed, things like that. So I ran the experiment with this frequency counter in, is the servicing necessary? Well, I measured some capacitors, things like that, and capacitors are usually the change out what's necessary to change to keep a unit like this working. And in this case, I got it functioning, got the switches cleaned up the unit, tossed it on the shelf to see if it was going to behave. Short answer is it didn't. It worked, people saw it, and I used it in several videos, but it's had some nagging issues, which I'm pretty sure are power supply related. See if we can get it to do it here on camera. Probably not, because I'm talking about it. Now, the specific issue was a startup from cold. So if I had the unit off for a while and I kicked it to start it, it would not start. Now, since I have the camera going and I'm recording this, even though this unit is cold, it's going to probably behave because I'm trying to demonstrate something, and that's just the way these things kind of go. Do need to turn it to the internal standard, so it does get a clock. If you have this unit set to an external standard, it's a switch on the back, that's the core clock for the entire frequency counter. So if it doesn't see a clock signal, the CPU doesn't even run. Everything is derived off the internal clock on this particular unit. So now that we're back to the internal standard, and I should also note that the fault in question does not work whether you're on the internal standard or the external standard. It still faults out and doesn't work. Let's see if it faults out. No, it didn't. So when it does fault out, the counter doesn't come up and it doesn't come into ARM. It just stays at that. I'll show you guys here in a second. It just stays at this screen right here and doesn't actually finish booting. Nope. Now it's going to behave, like I said. To get it past that point, all we did was turn off the power, turn it back on real fast, and it kicked over and operated just fine. So it's, like I said, it's a weird fault, and it did show up very, very repeatedly. The other thing that I didn't realize when I worked on this frequency counter the first time was this is a very, very early example of switch mode power supplies. Because this has a big chunky transformer in it and everything like that. I'm like, oh, linear supply, no big deal. This actually has a early switcher in it. Two of the power supply cards, they're about here in the unit. They actually do have a switching transformer and are switching supplies. So those caps have seen a lot of abuse and do need to be changed out. Switching power supplies, just by the nature of how they work, are pretty harsh on the output filters. That's by design, just the way they function. So we're going to get this thing opened up, get this serviced, and then hopefully this goes back on the bench for quite some time. I should also state that nothing in the lab is shelf queens. Everything that's on the bench, all of it functions, all of it works. There's one exception right now, which I am working on still, and there will probably be videos about it, but everything that you see on the bench in camera and everything like that, it's all been repaired, gone through, aligned and calibrated to the best of my ability, sometimes beyond factory calibration, but it's at least meeting factory specification as best as I can measure it. Actually, the channel in its entirety is that process. I think we're up to 200 something videos now of going through each piece of equipment and getting it ready to be put on the bench, because all this stuff gets used, and all this stuff gets used pretty much daily. And here we go, the insides with the covers off. Our two power supplies are here, which is going to be primarily the focus of this video. But as you guys can see, there's a giant transformer right here, big chunky thing. And that's the That was why I thought it had linear supplies in the beginning, because, I mean, it's got a pretty hefty sized chunk of iron in there. And turns out it's got both. So it needs some service. Let me flip this up real quick, and I'll show you the clock. The clock and reference for this particular unit is right in here. This is going to be a thermally isolated crystal, and it's thermally isolated by getting it above room temperature, is how these things usually work. We got a lot of boards here. We're going to need to check for electrolytic capacitors, but this guy is going to get a capacitor refresh. The thing that's wild about this is if I let this warm up, this crystal is still amazingly accurate for today. Measuring it against my rubidium, it is pretty much spot on. So great frequency counter, still in calibration as we tested it and measured it. It just needs some power supply work. And the lab has many treasures hidden off camera. And I happen to have a spare power supply board for this particular unit. But one of the things that's pretty interesting is we have a very old version, tell by the style of the capacitors. These are 2200 microfarad capacitors at, what are these, 30 volts DC, so not too bad, but I believe it's a 25 volt supply, so 30 volts is a little light, but not terrible. It's either 25 or 15 volts, I'm not sure. We have, well, it's going to be 15 because these are 20 volt caps. So we actually have a bump up in capacitance to 5600 microfarads at 20 volts DC. No, those are in parallel. So we're going to be additively upping that capacitance. So 44, let's see, that would be 80, call it 8800 microfarad in this capacitor channel. So they added, or HP increased the capacitance significantly from 8800 microfarad to 16,800 microfarad. So they almost doubled it on the power supply rail, probably to keep it quiet. So lots of work to do on this board. This cap gets to stay. This capacitor down here gets to stay. This is going to be a hermetically sealed glass encapsulated tantalum capacitor, so that gets to hang out. But these electrolytics are going to get replaced. The switching transformers are actually in these cubes. So, and then we have regulators and drive elements mounted to the heatsink in the back. So neat little power supply board, but does need a little bit of help. Okay, let's talk about this power supply. Well, I should have done this a long time ago, and this is just going to prove something out. Also, in my original assessment, the math was a little messed up. So here's the old power supply. Here's the new power supply. Yeah, we did add capacitors, except the polarities are backwards on these. So it's 44 microfarads and 44 microfarads for the positive and negative supplies. Actually, that was backwards. This is negative. I believe this is negative. That's positive. If we flip it over, we can actually see positive 14 volt, negative 14 volt. And actually, this one's different. This is 22 volt. So these supplies are not interchangeable for sure on the units, because this is a 22 volt supply. This is actually a 14 volt supply. Plus 14, minus 14. So we have increased the capacitance a little bit more. We got 6,800 microfarads at 25 volts on a 14 volt supply. Those will live all day long. These were 5,600 at 20, so we gave it 5 more volts and a little bit more capacitance. These guys are the ones I want to talk about. These are 330 microfarad by 20 volt, and these are Sangamo. And if there was any question as to was this necessary, was this not necessary, oh, these are so bad. So I have them hooked up on the ESR tester, and we'll hit go. This is just a random one that I pulled out. So we got 14 ohms of ESR, which isn't terrible, but we have 592 microfarads of capacitance. Now, the meter's lying. This is not a 592 microfarad capacitor. This is a DC leaky capacitor and is absolutely failing this test and needs to go. So if I thought the power supply was good. These were awfully bad. These weren't so great either in terms of DC leakage. Worse ESR, but it is also a bigger cap, so that's kind of normal. But I have 6272 on a 5600. This one's toast too. Now I could actually hear that while the unit was running after I pulled it off the bench, because these transformers were starting to squeal. They were starting to squeal because they were under stress because these caps weren't building voltage correctly and were drawing too much current. So absolutely this board needed to be repaired. This capacitor, which is from this position right here, is absolutely massive at 9100 microfarads at 12 volts. So this is now a 10,000 microfarad at 25 volts. So, and all of these are 105 degree C rated caps, extremely long life. These will live for quite some time on this power supply. This one's ready to go back in. I got to get the other power board out and do the same thing. I totally grabbed the wrong board while I was working on the supplies. So it's actually got two supplies. One is a 22 volt unregulated, regulated. The other one is a 14 volt regulated. The 14 volt regulated has 5600 microfarad capacitors in it. The 22 volt board has the smaller caps in it. I don't know what I was thinking earlier in the video, but yeah, it does look like the boards are interchangeable actually, because the layout is exactly the same. I wouldn't risk it, but it does look like it might work. There was some updating because of the tantalum capacitors and a couple of other things on the older style board versus the newer style board. But we have a 22 volt board and a 14 volt board. So it is easy to get turned around in this thing. This is the 14 volt board from the from the lab. This is the 22 volt board that I need to rebuild. And here is the 22 volt board from the lab stockpile. So easy enough to get turned around, but we're making progress, and here we go. I apparently need more coffee. Okay, here's our board with the replaced capacitors. These were a little tougher to get in there than I thought. We bumped up the capacitance, and I did have to do some rewiring. They were slightly larger, and this is a power resistor, so I had to keep them away from that. They are mounted to the board. They're not going anywhere. So there's a solvent. If I need to, I can break those free at a later point in time, and they are actually clearanced, so we will not have a clearance problem with the pocket that they have to go in. Very, very, very limited on space because this board has to slide in here. So if I did my job right, I'm ready to turn this thing on, and if I did my job right, we won't have any bright flashes and bad things happening. Well, I didn't have the camera running, and I plugged it in, and it was turned on, and immediately the fuse went, and stuff started to smoke out. So I did something wrong. Famous last words. I saw smoke coming from this area, and needed to, and then the fuse went, and it died. So what ended up happening, as we can see, it's armed. Let's see if it can count still, or if we catastrophically caused some problems. We'll do 1 VRMS into 1 megohm, AC coupled 10x attenuator, and 1 megohm into channel A. Let's see if it'll count. It does. Okay, so we didn't hurt the counter, thank God. However, I did wire these two capacitors backwards. They're bulged up. So these are the two caps that have a problem, and they're still hot. So I got to pop these off a little quicker than I was expecting, but I got to flip them around polarity-wise, and we'll work on going from there. Okay, two new capacitors in the correct polarity this time. Here are the old ones. They're nice and domed up and very bad, which is unfortunate because these were not inexpensive capacitors for their size. And those only had 22 volts across them, and they're 63 volt caps, and they went away in about 30 seconds. So they got hot fast. Of course, short circuits do that to things as it draws quite a bit of current. So let me get the frequency counter back up here on the bench, and we will see if we can't get it started up. Made sure it was off this time before plugging it into power, so you guys get to see the power up, just in case there's any more excitement. Hopefully not. We've had enough for this video. And we went to ARM. Okay. So we're back to where we were, and it's all right since we changed capacitor values. I don't expect it to fire up instantly. We're drawing about 120 watts while it's on. That's not necessarily a problem. A little hot for a frequency counter, but it's also old. Let me get my amplifier. Here it is. I have an amplifier that we're going to plug into the external. We'll put the cover back on, plug in this to the external, and then see if we can't get it fired up on the external, and then let it burn in for a while, see what kind of counts it gives us. All right, covers are on. External set up, not turned on, so we're going to get to see some interesting cases, and that's okay. All right. It's going to sit here for a little bit because I don't have the amplifier turned on, so there's no clock. So this is what it was doing before. It was just kind of hanging out and wasn't working very well. I'll turn the clock on. And if it picks it up, might need a bit more. All right, let's hook up a scope and and see if we have enough input going in. This may need more signal. The lab is just fighting tonight. It helps when you wire the amplifier in the correct way. I had the output on the in and the in on the out, so it's not going to work. Let's see if it works now. There we go. Okay, we're on the rubidium standard. That's what it's supposed to be doing. Let's see how accurate we are. And I definitely need to see how accurate we are after stressing the power supply like that. That could cause some shift in frequency. All right, so I'm asking for 50 megahertz out of the function generator, sine wave, into the counter with 1 volt RMS. Well, that looks pretty good. That's a long gate. 50.066. That is not half bad, and we're on the external standard. So as it warms up, we'll see if it counts a little bit better. It's actually coming down, so I expect this to drift a little bit closer. So I'm going to leave this on for a while, let it warm up, do some burn-in testing, let the function generator shout into this. Function generator we're using is the Rigol 4162. And that is actually hooked up to the rubidium as well, so we're on the same clock, just to make sure it is. Utility. No, we're not, actually. Clock source is internal. So system, clock source, external, detected a valid external clock. And we go back to sine wave. Let's see if this gets even more accurate now. So the Rigol's off by about 66 megahertz from the rubidium. The rubidium, it would be much more accurate, which is why I have it on an external clock. Not really sure why it didn't pick it up, because it usually does. But that is also why we check these things. All right, so burn-in test type times 2, and we'll see what happens. All right, well, it's been running for quite some time, and absolutely, we are rock solid at 50 megahertz. Everything is good to go. The external power supply, or the external input's working a lot better, and the frequency counter is much better behaved. So this one's ready now to go back on the shelf and actually really put in some work in the lab. Should have done the power supply when I had it open the first time, but did the experiment, and we now have the results. As I was cleaning up, I realized the dish of shame is quite a bit bigger than normal. There was a lot of caps that had to come out of this thing. Yeah, it definitely needed some help. And from the testing, these were very bad. So, thanks for stopping by the lab. Sorry about a little bit of the disjointedness of this video. I have told the patrons and the members that if I hit the record button on the camera, regardless of what happens, you guys see the real things that happen here in the lab, even when I'm wrong. So, everything goes up on YouTube. If it gets recorded, it's on its way up to the internet. So that is something that I do think is important, is it's not always perfect. Actually, it's there's quite a bit that can go wrong in a repair or a restoration. So we just have to deal with it as it happens. But that's part of the fun. So if you like what you see, hit all the YouTube buttons, like, subscribe, and share. And thanks again for the patrons and the members who help keep the lights on here in the lab and videos coming up to YouTube. With that, as always, check out the Patreon page if you're interested. And I will see everybody in the next video. Bye for now.